Here are the solutions to the book problems from section 10.4 for calculus. This is a real quick assignment. You can make quick work of this with a couple pieces of knowledge that you gained from the notes here, and that is your knowledge of p-series, what p-series do, and also your knowledge, albeit, let's say, casual knowledge of the limit comparison test. I say casual knowledge because we haven't formally learned what the limit comparison test is. We'll do that in section 10.5. Just as a point of fact, in the 2016 administration of the AP test, you guys are the last group that does not need to know formally the limit comparison test. They're adding that to our curriculum next year. I've always taught it, but it probably is a good thing for you to know that your sort of casual knowledge of it, like how we're going to use it in this section, these problems here, is really just what you need to know about the limit comparison test. And we will go over it in more detail in 10.5, but and also, if just in case you're watching this video in some subsequent year, if you're taking the test in 2017 or beyond, then you do need to be familiar with the more formal definition of the limit comparison test to understand that. So, blah, blah, blah. Let's get started. Number 3, ABCD. We just have 4 series here, and they're all p-series. So we just have to identify what the p is and determine whether the series converges or not. So just to make sure that we're familiar with that. So in A, I'm not going to recopy the actual series. But in A, the p is 3, and if the p is greater than 1, then it converges. In B, slightly in disguise, but can't fool you guys. That's just a p-series with a p of 1/2. P is less than 1, so that diverges. C, the p is, don't be fooled here, the p is not -1, not that it would change the answer, but the p is 1, right? That's really 1 over k. So the p is that p, is it greater than or less than? I guess I should say here, if the p is less than or equal to 1, then it diverges. So since the p is less than or equal to 1 in this case, it diverges. In fact, that's the harmonic series, right? And in D, we have a p of 2/3, not -2/3, right? The p is the exponent as it shows up on the bottom. So that p is less than or equal to 1, so it diverges. Seems easy, but of course you have to remember that, right? And I'll just note that how do we know this about p-series? The reason that we know this is because of the integral test. It's the integral test that gives us this result. All right, what's next? Number 9 through 13. So, number 9, we have a series k equals 1 to infinity of 1 over k plus 6. And by our knowledge of the limit comparison test, 1 over k plus 6 behaves like 1 over k, right? We treat that like a limit, and that really just behaves like 1 over k. And so that means it's like a p-series where p is 1, so that diverges. And you could also think of this, if you start plugging in those numbers, you get 1 over 7 plus 1 over 8 plus 1 over 9, etc. That's like the harmonic series with the first few terms cut off. But if it's going to diverge eventually, then if you cut off some finite number of terms at the beginning, it doesn't make any difference. It's still going to diverge, right? It's like what's infinity minus some number, still infinity. Number 10. We have the sum k equals 1 to infinity of 3 over 5k. And just like with limits, just like with integrals, because integrals are, after all, defined in terms of limits, if there's a constant in there, you can pull that out to the front. That's the same thing, because the 3 over 5k, that's going to happen to every single term, so you could factor it out to the outside. And of course, that's the harmonic series, so that diverges. Number 11, we have the series k equals 1 to infinity of 1 over the square root of k plus 5. And that is, by limit comparison, like the series 1 over k to the 1/2. And so that's like a p-series where p is 1/2, and that's less than or equal to 1, so that diverges. A lot of divergence going on here. Number 12 is a little trickier, maybe the trickier of the lot here, because it's not a p-series. We're going to think about what's going on here. I'm going to write this as e. The kth root of e is the same as e to the 1 over k. Now, what happens to e to the 1 over k as k approaches infinity? Well, 1 over k as k approaches infinity is going to approach 0. So the bottom here is going to approach e to the 0, which is 1. So since the terms, the a sub k terms, are going to approach 1, right? As k goes off to infinity, this is going to get closer and closer to 1 over 1. Or maybe it would be better, that's a sort of series way of saying that. It's the same as saying the limit as k approaches infinity of 1 over e to the 1 over k is equal to 1. That's what's happening to the terms. So if the terms are going to 1 over 1, this diverges because of the divergence test. Right? Remember, for a series to have any chance at all of converging, the terms have to approach 0, right? For any chance of convergence. And just to drive the point home, if the terms are going to 0, does that mean it converges? No, it doesn't, because in the harmonic series, for example, the terms are going to 0, but it still diverges. So this is just a test to see if you have a chance. It's really just a way of saying, you know what, if they're not even going to 0, then there's no chance. Right, so this diverges because the terms are getting closer and closer to 1. So that means as you go further and further out in this series, it becomes more like plus 1, plus 1, plus 1, plus 1, and that's obviously going to diverge. Number 13, got another limit comparison type situation here. I have 1 over the cube root of 2k minus 1. So all constants really fade off into insignificance here. So the thing that really matters is the power of k here. This is going to behave like 1 over k to the 1/3 power. the constant multiple here, that doesn't matter. If it converges or diverges and you multiply it by the cube root of 2, it doesn't make any difference, right? It's still going to behave the same way. So that is a p-series where p is equal to 1/3, and that's less than or equal to 1, so that, once again, diverges. A lot of diverges here. And what are we doing? One more? No, two more. 18 and 20. Maybe we'll get some convergence here. 18. Oh, no, not in this one. So k equals 1 to infinity. And this time we have k squared plus 1 over k squared plus 3. You could say, I guess, that that's like a p-series with a p of 0, right? Because you look at the highest exponents. It would be like k to the 0 on the bottom. Or you could also say, I think this is a little bit better, since the limit as k approaches infinity of the terms, that's an easy pre-calc kind of limit, highest power, top, bottom, coefficients 1 over 1. So that approaches 1. And that means as you go off to infinity, this gets closer and closer to 1 plus 1 plus 1 plus 1 plus 1, and that diverges just by the divergence test. Although I do think it's okay to think of that as a p-series with a p of 0. That makes sense too. And then last, we have 1 over the square root of k squared plus 1. And here, that's going to behave like a p-series with 1 over the square root of k squared. It's like 1 over k. And that's p-series with a p of 1. That's the harmonic series with a p of 1. And that diverges. So, a lot of divergence there. So you know, I think the book was expecting, because I think the book didn't really expect you to know anything about the limit comparison test yet. So they were thinking that you would actually do these problems. Let's see, this one, that one's trickier. This one, maybe not that one. That one probably divergence. But a lot of these, they were probably expecting that you would use the integral test and actually do the integral. But we know, because we have a little bit of advanced knowledge of limit comparison, that because the integral test gave us this knowledge about p-series, we can apply that in lots of different situations using limit comparison. And that's it.